So let's see Pauli's exclusion principle. So actually what is Pauli's exclusion principle is no two electrons can have all the four quantum numbers same. So no two electrons can have all the four quantum numbers same. So this is that principle, Pauli's exclusion principle. So that one, now here in quantum mechanics we are proving this principle. So how is this principle is possible? So what makes up this principle? So has the this is related to atomic level, that is microscopic level, microscopic world, that is electrons. No two electrons can have all the four quantum numbers same. So it is related to microscopic world. So quantum mechanics mainly deals with such microscopic world. So we will see how is this possible in this topic. So actually, to define an electron, so suppose this is atom, it is nucleus, and these are the electrons. So this is one electron and this is some other electron, like that. So to give a complete each electron is defined by certain set of quantum numbers. So to define the position of the electron, so to in which state the electron is, so in the atom, inside the atom, in which state the electron is in. So in order to define that, we need four quantum numbers. So that is first one is principal quantum number, that is n, gives us information about distance of the electron from the orbit. So just like K shell, L shell, M shell, like that, we have 1, 2, 3. The value of n ranges from 1 to 3, like that. And next one is azimuthal quantum number. Gives about this one gives information about the orbitals of the electron. So that is where the probability of finding electron is more. So it gives depending upon shapes of the orbitals, we can see that. So this is that number which gives information about shape of the orbitals. So that is s orbital, p orbital, d orbital, and this one starts from n minus 1. For a given n, it has n minus 1. That means its value start from 0, 1, 2, like that, and so on. And for the first shell, we have 1s, and we don't have 1p, like that. And for the second shell, we have 2s, 2p. So it would have uh, n minus 1 value. So for second shell, n value is 2. So 2 minus 1 is nothing but p. So like that. And for the third shell, we have 3s, 3p, 3d. So like that. And next thing is magnetic quantum number. So it has 2l plus 1 values, and it this one gives the information about orientation of the electron, in which way the electron is orienting. So orientation means, for example, suppose we are holding a ring on the hand. So this ring, suppose if we are holding a ring in our hands, so we can tilt the ring so at certain angle. So right hand side up and left hand side down, like this, and left hand side up, right hand side down, like that. We can tilt this ring. So this changes the orientation of the ring. So we can also hold it like this in vertical position, like that. So in the same manner, in which manner the orbit of electron is, so whether it is in this angle or in this angle, or whether it is rotating in this way, so like that. So it gives us information about the orientation. So it is the it is affected by, as it is affected by magnetic field. So if we apply magnetic field, this uh, electrons orientation would change. So for a different, suppose we need to distract the electron in the direction of magnetic field, so different energies are required. So like that. So we have a magnetic quantum number. It has 2l plus 1 possible values. That is So for if L is 0, so 2 into 0 plus 1, 1, one possible value, that is 0. And if L is 1, 2 plus 1, that is 3, 3 possible values, that is minus 1, 0, 1. For a given value P is equals to L. So hence we are having Px, Py, Pz like that. So we are only having S orbital Px, Py, Pz, and in the case of when L value is 2, 2 2s are 4 plus 1, 5. Hence we are having 5 d orbitals, that is dxy, dyz, dzx, and dx square, y square, and dz square like that. So based on this, and last and final quantum number is spin quantum number. So it gives us information about the spin of the electron. So these are all the four quantum numbers. So whether the electron is spinning up or down direction, so in which whether it is spinning in clockwise or anti-clockwise like that. So all these information, all these four quantum numbers are required in order to define the state of a particular electron in an atom. So what the Pauli's exclusion principle says is that no two electrons can have all the four quantum numbers same. So that one you are seeing now. So it has been shown that if psi of 1 comma 2 is the solution of Schrodinger equation, then psi dash of 1 comma 2 is equals to a into psi of 1 comma 2 plus b into psi of 2 comma 1 is also the solution of Schrodinger's equation. So if we consider the case of identical particles, so electrons are identical particles. So if psi of 1 comma 2 is thus a wave function, that is it is the solution of a given Schrodinger equation, then if we change in the place of first electron, if we shift second electron, and in the place of second electron if we keep place one electron, that means if we interchange their position, then that is also the solution, that also would be the solution of Schrodinger equation. And not only that, a linear combination of these both, so psi of 1 comma 2 and psi of 2 comma 1, so 2 factorial permutations are possible for two particles. So in addition to that, linear combination, their linear combination would also be the solution of Schrodinger equation. So this point had been discussed in symmetric and antisymmetric wave functions, construction of symmetric and antisymmetric wave function. So from that we used to get this point. So if psi of 1 comma 2 is the solution of Schrodinger equation, then this linear combination of psi of 1 comma 2, psi of 2 comma 1. So here we are multiplying with a, and this is multiplied with b, and we are adding them. So this is a type of linear combination of psi of 1 comma 2 and psi of 2 comma 1. So this wave function would also be the solution of Schrodinger's equation. Now since the particles are exactly identical, all physically measurable quantities must be independent of exchange of any pair of two particles, that is we must have. So as these particles are identical, so if we place suppose in the starting we suppose this is one first electron and this is second electron, and if we in the place of first electron we keep second electron, in the place of second electron we keep first electron, then also the properties, physically measurable quantities would not change. That is because of the identical nature of the electrons. That only if we interchange electron and positron, then immediately we can see the difference in the physical quantities. But here we are interchanging these electrons, they are just identical to each other. So in that case physically measurable quantities would remain the same. So one of those quantities is probability. So xi into xi star is nothing but probability density, that is in modulus of xi dash of 1 comma 2 whole square. So that is nothing but probability of finding the electron, that is probability density. So that property also would not change. So that is the meaning. So xi dash, so if xi dash of 1 comma 2 modulus whole square is equal to xi dash of 2 comma 1 whole square, that means if we in the place of 1 if we keep 2, in the place of 2 we keep 1, then that also would give us the same probability. That means if we interchange those two electron, first and second electron, if we interchange, then also the probability density would not change. So that is the meaning of this equation. This implies that A is equal to plus or minus B. So this case is possible only when A is equal to plus or minus B, or else B is equal to plus or minus A. So in the place of B if we place plus or minus A, so this condition would be satisfied only when A is also plus or minus me. then only this condition would be satisfied. Xi into xi star, that means this wave function multiplied with its complex conjugate, and this wave function could be obtained by replacing in the place of 1 by 2 and 2 by 1. So for same wave function, if 1 is replaced with 2 and 2 is replaced with 1, we get the some wave function. So that wave function would also be uh, equal to this. We find the probability densities. So hence we are having A is also plus or minus B. That is, in the place of B, we replace it with plus or minus A. So we would have this from equation 1. So just like for symmetric wave function, we would add these two, xi of 1 comma 2 plus xi of 2 comma 1. And for the antisymmetric wave function, we would subtract them. That is xi of 1 comma 2 minus xi of 2 comma 1. In such a manner, this is. So finally, we would have xi dash of 1 comma 2 has B is replaced with plus or minus A. So we would have this overall equation. The Hamiltonian function for the system of two particles is, so if we consider the system of two particles, in that case Hamiltonian is nothing but total energy. So total energy would be in the form of kinetic energy and potential energy. So as there are two particles, so kinetic energy of first particle, that is half mv square. If you multiply and divide with m, and we would get m square v square by 2m, that is mv is nothing but momentum. So hence you are having p1 square by 2m. This is the kinetic energy of first particle, and this is the potential energy of that first particle, and this is the kinetic energy of second particle, and this is the potential energy of that second particle. So overall Hamiltonian for a system of two particles is this. And the operator, so if we in quantum mechanics, we mainly used to deal with operators for everything. Yeah, position operator, momentum operator, energy operator, like that. So Hamiltonian operator can be written as, if in the place of P, so P is actually nothing but minus I h cut del for a three-dimensional. So if we consider for one dimension, it is Px is equals to minus I h cut dou by dou x. This is for one dimension, and this is for three dimensions. So minus I h cut dou delta. So in the place of P1, we need to replace with minus I h cut delta. So if we do square of that, minus into minus is plus, but I square is minus. So here where confusion arises. So P square is nothing but minus into minus plus I square is minus. So minus h cut square del square. So minus h cut square del 1 square. So we would have finally minus only. So minus h cut square by 2m del 1 square, and v1 here also minus h cut square by 2m del 2 square plus v of 2. So here confusion should not arise. Minus I whole square is nothing but minus 1 into I whole square. So minus 1 whole square is 1 and I square is minus 1. So overall we would have minus 1. So and h is equals to h1 plus h2. So from this we can see easily that this is the Hamiltonian of first particle and this is the Hamiltonian of second particle, and hence the Hamiltonian operator for the system can be written as h1 cap plus h2 cap. And the Hamiltonian function for the system of two particles is the sum of the Hamiltonian functions for individual particles. That is this part they are saying. So this happens when we assume that identical particles do not interact, and if they do, then the interaction is very feeble. So this is the case when we think that the identical particles do not interact. That means the two electrons inside the atom, they are not interacting with each other. So they are independent of each other. They are not influencing each other in such a manner if we take. So then this case is possible. But actually there would be some interaction between the two electrons. The two electrons would repel also. So here we are just neglecting that interaction. So if we consider the interaction is very feeble, in such a case, this is the Hamiltonian. And so when the Hamiltonian function for the two particles is separable, the energy eigenfunction for the entire system expressed as the product of eigenfunctions for individual particles. So if the Hamiltonian function is expressed as sum of the Hamiltonian functions of individual particle, then the eigenfunction of the system could be represented as product of eigenfunctions of individual particles. Hence we are having xi of 1 comma 2 is equal to xi of 1 into xi of 2. So the next thing is Since the two particles are exactly identical, they are acted upon by the same force, and hence v of 1 and v of 2 have the same analytical form, indicating thereby that wave functions belong to same family. So here, as we have already discussed, we are considering the case of identical particles, as they both are identical and they are acted upon by the same forces and hence have the same form, identical nature. So same force is acting on both the particles, so those forces would have the same form. Now the wave functions belong to the same family. Let xi n of I denote the normalized eigenfunction for the ith particle. The n indicates the complete set of quantum numbers needed to describe a state. So we can write equation 7 as. So next thing they are considering is let xi n of I denote normalized eigenfunction. So if this is a normalized means integration of xi into xi star d tau is equals to 1. So if we get integration of xi into xi star d tau is equals to some value constant, then it is unnormalized. The normalized eigenfunction for the ith particle where n indicates. So here this is the eigenfunction for the ith particle. So it may be first particle, second particle, third particle, like that. So for the ith particle, and n is the complete set of quantum numbers needed to define that particle. So all the 4 quantum numbers which are required to define that position, that situation of the particle, the state of that particle. So that is the n to describe a state. So we can write equation 7 as. So equation 7, this is equation 7, could be written as xi of 1 comma 2 is also xi of n1 of 1, xi of n2 of 2. This means first particle is in the first particle's eigenstate is, that is has first particle's quantum numbers are n1 and second particle's set of quantum numbers are n2. So for every electron we would have a possible set of quantum numbers to define that electron. So each electron has its own set of quantum numbers. For suppose we take the case of helium atom. For helium atom 1s2, this is the case. This is one electron, this is another electron. If we consider the case of this electron, n is equals to 1 because it is in the first shell, and L is equals to 0 because it is s orbital, and m is equals to 0 because 2 into 0 plus 1, that is only one possible value, and spin is equals to half. And for the second electron, if we see, it is also having n is equals to 1. It is also residing in the first shell, and it is also residing in the s orbital, and its magnetic quantum number is also 0. For this particular value of L, only one possible value of m is possible. It is 2 into 0 plus 1, 1. And so we would have, in this case, s is here already, s is equals to half is there. Here already n is equals to 1, here also n is equals to 1. Here L equals to 0, here L equals to 0. Here m equals to 0, here m equals to 0. But Pauli's exclusion principle says that no two electrons can have all the 4 quantum numbers same. So for these 2 electrons, these 3 quantum numbers are all the same. So the 4th quantum number for this electron definitely should change. So hence it is spin is minus half. So hence we used to initial if we want to fill with 2 electrons, one of the electrons would be pointing up, another is pointing down. So y means it is of plus half spin, this is of minus half spin, because both electrons are having all these 3 quantum numbers same. They must differ in one quantum number, and that is spin quantum number here. In the same manner, if you consider the case of lithium, so its electronic configuration, hydrogen, helium, lithium. So its electronic configuration is this. It has 3 electrons. So this is for first 1s orbital, and this is for 2s orbital. So if we consider these 2 electrons now, you see here its n value is 1, and L value is 0, and m value is also 0 for, and spin is half. And for this electron, n is equals to 2, L value is 0, M value is also 0, and spin is also half, because it is also pointing up, it is also pointing up. So where they are differing here is in this case, n is equals to 1, n is equals to 2. So in this case it is in its n value is 1, principal quantum number is 1. For this electron its principal quantum number is 2. So they are differing over here. So thus, for any no two electrons can have all the four quantum numbers same. So that is impossible. So that is the Pauli's exclusion principle, and this is nothing but set of quantum numbers required to define the state of this electron. So here n is nothing but n1 is nothing but set of all those quantum numbers which define the state of that particular electron, and n2 is the set of all those quantum numbers of that second electron which defines its position in the atom, like that. So the above wave function describes the state in which the particle 1 is in the state, describes the set of quantum numbers n1 and n2 state described. So that is the thing they are saying. So particle 2 is in the state described by n2. So second electron is in n2 state and first electron is in n1 state. But since the particles are identical, particle 1 may be in the state n2 and 2 may be in the state n1, and also that. So as the two particles are identical, so if they exchange their position, then also we cannot find the difference. So then also they would look the same as before. So that one they are saying. And also that xi of 1 comma 2 is equals to plus or minus xi of 2 comma 1. So we have. So another thing is, if we interchange these two particles, the wave function may remain the same. So that is symmetric wave function. Then we would have plus xi of 1 comma 2 is equals to plus of xi of 2 comma 1. So this is the case for symmetric wave function. That only if we interchange the two particles, we would have minus xi of 2 comma 1. So the sign of the wave function changes. So that is the case of antisymmetric wave function. So now xi dash of 1 comma 2 a into, so this is from this equation. Xi dash of 1 comma 2, xi of 1 comma 2 plus or minus xi of 2 comma 1. So a is as usual. So xi of 1 comma 2 is replaced with xi n1 of 1, xi n2 of 2, and xi of 2 comma 1 is replaced with xi n1 of 2, xi n2 of 1. So what does this mean? So here the first particle is in the state n1 and second particle is in the state n2, but here second particle is in the state n1 and first particle is in the state n2, because they are identical. We cannot find any difference. So xi dash of 1 comma 2 is equal to a into xi of 1 comma 2 plus xi of 2 comma 1 plus or minus xi of 2 comma 1. So just writing this equation. So the above expression is same as expression 3. So this expression is same as this expression C, and the wave function xi dash of 1 comma 2 describes the state in which one particle is in the state n1 and another particle is in the state n2. So and no matter which particle is in which state, the probability of occupying any state by any particle is equally likely. So whether the first particle is in state 1 or the first particle is in the state 2, so that probability is equally likely, they are saying. Why means both of these particles are identical, so the probability would be equally likely. So for Fermi particles, equation 9 can be written as, so this is equation 9. So for Fermi particle means fermions. So fermions follow antisymmetric wave function. So we would have minus sign here. So for Fermi particles, xi dash of 1 comma 2 is equals to a into xi n1 of 1, xi n2 of 2 minus xi n1 of 2, xi n2 of 1. So this is the case for the fermions. So in the case of bosons, it would follow symmetric wave function, then we would have plus here. And xi dash star of 1 comma 2. So if we take the conjugate of this equation, then a into xi n1 of star 1 star of 1 and xi n2 star of 2 minus xi n1 star of 2, xi n2 star of 1. So that means we are just taking complex conjugate on both sides. So this complex conjugate is this. The complex conjugate of this wave function is this, and for this is the complex conjugate. So that is from by taking complex conjugate, and the condition integration of xi dash of 1 comma 2 into xi star of 1 comma 2 d tau is equals to 1. So this condition finally what does it gives us is a square is equals to 1 by 2. That means we need to multiply this both and integrate it over the d tau entire space. So if you multiply, what we would get is a into a square, and this one multiplied with this one and integration d tau would give us 1, and this one multiplied with this one minus into minus plus xi1 star of 2 xi1 and of 2. So this both multiply, that also would give us 1. That only this cross multiplication would be subtracted. So here we would have it would be so in cross multiplication integration of xi I xi j d tau is equals to 1 when I is equals to j, and 0 when I is not equal to j. So in this case if we do here n2 is there, here n1 is there for second particle, here for the first particle n1 is there, n1 state is there, here n2 star state is there. So because of based on orthonormality condition, this two that remaining two terms would be vanished. So only what would remain is this both multiplied would give 1, this both would multiply would give us 1, minus into minus plus 1. So 1 plus a square into 1 plus 1, that is 2a square. So 2a square is equals to 1 based on this condition. So a square is nothing but 1 by 2, that is a is 1 by root 2. So therefore the system of two particles described by the antisymmetric state is written as, so for the two particles, so finally we have found the value of a also. So we just need to substitute this value in this equation. So this is the system of two particles described by the antisymmetric state. So that is for the fermions. Now if we see from this equation, if n1 is equals to n2, that is the two particles have the same quantum state, the resultant state disappears, and we conclude that probability of two antisymmetric identical particles is 0. Two non-interacting fermions cannot be both in the same quantum state. So in this equation, if we replace n2 equals to, that is if we consider n1 is equals to n2, so in the place of n2 if we replace it with n1, so xn1 of 1 into xn1 of 2 minus xn1 of 2 into xn1 of 1, it is just like ab minus ba, that is nothing but ab minus ab, that is equals to 0. So because of this minus sign, this wave function would not exist. So when both the states are equal, that means when the two quantum states of two electrons are the same, then in such a case the eigenfunction does not exist, it vanishes. That means no two electrons can have all the four quantum numbers same. So that is the Pauli's exclusion principle. And here we have considered it for the case of two electrons. So now let us see for a system of n particle system. So that is for two particle system, and if we consider the n particle system, Schrodinger's time dependent equation for a system of n particles is written as, so for a system of n particles, Schrodinger's time dependent equation, that is h xi is equals to I h cut dou xi by dou t, h xi is equals to I h cut dou xi by dou t, as we are considering taking time term, hence it is Schrodinger's time dependent equation, as we are considering the taking the time term here. So xi is a function of, so n particles are there, so 1 2 3 are some particular r particle, s particle, n particle and t. So as this is a Schrodinger's time dependent equation, wave function is depending on time also. So h of so Hamiltonian for the system would depend on all the n particles. So h of 1, h cap of 1 2 3 and so on n, and xi, so it is just nothing but h xi is equals to I h cut dou xi by dou t. We are just representing, so what it is a function of so and so like that. Now if we permute the argument of xi in any equation, in any way, so if we permute, that means we rearrange these particles, that means if we exchange two particles. Suppose here what they are doing is R and S are two particles. So in the place of rth particle we are replacing with S, and in the place of sth particle we are replacing with R. So that is the thing they are doing. So they are permuting. So 1 2 3 S R N comma T, and here wave function also 1 2 3 R S N T. So actually here S and R should come. So if we exchange any two particles, then this is the equation. So this resulting solution is also the solution of equation 1, as H is symmetric with respect to exchange of identical particles. So this is also one of the possible solution of this Schrodinger equation. Like this, n factorial solutions can be obtained from n factorial permutations of an argument of psi. So this point has already been discussed in construction of symmetric and antisymmetric wave functions. So if there are two particles, then there would be two factorial possible permutations, that is psi of 1 comma 2, psi of 2 comma 1. So two factorial possible solutions, and here n particles are there, so n factorial possible permutations and n factorial possible solutions would be there. And also any linear combination of these functions is also a solution of the wave function. So if we consider the linear combination, just we have considered before, a into psi of 1 comma 2 plus b into psi of 2 comma 1, like that. So that linear combination would also be the wave function, would be the solution of this equation. The sum of these functions is a symmetric wave function, and the antisymmetric unnormalized wave function is constructed by adding together all the permuted functions resulting from even number of changes original and subtracting from this sum of all permuted arising from odd number of changes from the original solution. So as this point is also been discussed in symmetric and antisymmetric wave function construction. So symmetric wave function can be obtained by just adding all these possible n factorial solutions, just the sum of all of them. And antisymmetric wave function is adding up even permutations. So for one time we would exchange, and another time also we would exchange, then there we have exchanged it for two times, and if we exchange it for another time, then we have exchanged it for odd number of times. So the wave functions obtained by even number of interchanges, sum of all of them, subtracted by the wave functions obtained by odd number of exchanges. So that is nothing but antisymmetric wave function. So antisymmetric wave function cannot constructed from the solution that remains unchanged by the interchange of particles. So for a function to be antisymmetric, after the interchanging of particles, it should change. That is, sign of that function should change. So hence we would have psi of 1 comma 2 minus psi of 2 comma 1. Why means if we interchange the first and second particle, we would have minus of that wave function. So the wave function sign changes. So that is the thing they have mentioned, remains unchanged by the. So we cannot construct antisymmetric wave function one solution that remains unchanged, they are saying. So if the Hamiltonian does not involve time, so if we let us suppose Hamiltonian does not depend on time, then we would have h psi is equals to e psi. That is nothing but h psi e psi. If we take this e psi to this side, it would become minus e psi. So if psi is taken as common, we would have this. So h of 1 comma 2 comma 3 comma n minus e psi of 1 comma 2 comma and so on comma n equals to 0. So if we neglect interaction between individual particles, same as before, if we and the before case also we have neglected the interaction between those two electrons. So here also if we neglect interaction between these many electrons, suppose there are n electrons in an atom, so if we neglect all those repulsion between those electrons, so then we would have h naught of 1 comma 2 comma 3 and so on n is equal to h naught dash of 1 plus h naught dash of 2 plus and so on plus h naught dash of n. So this is the case. So all the Hamiltonians would be Hamiltonians of the n particles would be added up. So h naught of 1, 2 and so on comma n is unperturbed Hamiltonian for complete system. So this is unperturbed, that is undisturbed Hamiltonian, because we are neglecting the effects of interaction between two particles. and h naught dash of 1, h naught dash of 2 are the Hamiltonians for individual particles. So this is the case for single electrons. So this is the Hamiltonian for first electron, this is the Hamiltonian for second electron, this is for nth electron, like that. And this is for the overall all the electrons, all the system put together, that is the Hamiltonian. So if the Hamiltonian could be expressed as sum of the individual Hamiltonians, then the wave function can be represented as product of individual wave functions. So that is the case. So xi of 1 comma 2 comma 3 and so on could be written as xi of 1 into xi of 2 into xi of and so on comma xi of n. So in order to be specific, we would write it as xi n1 of 1 means first electron is in n1 state, and xi2 of n2, that means second electron is in n2 state. So these states gives us the information about quantum numbers of that particular electron, where n1, n2 and n1, nn indicate the totality of quantum numbers needed to represent a state. So E is equals to En1 plus En2 plus Enn. So total energy of the system would be the sum of energies of all the particles. Total energy of the system. Also h naught dash of 1, Zn1 of 1 is equals to En1, Zn1 of 1. So as we know that h xi is equals to E xi. So this is the case satisfied for each of the individual electrons. So this is for the first electron. On the same manner we would have for the second electron. So overall, so for the Fermi particles, the antisymmetric state is written as. So overall, if we see the antisymmetric wave function for the system of n particles, fermions, like electrons, could be written as xi. So xi a means antisymmetric of 1, 2, 3 and so on, n is equals to 1 by n factorial determinant of n1 of 1, n1 of 2, n1 of n, and n2 of 1, n2 of 2, and 2 of n. That means, so first particle in state n1, second particle in state n2, and n1, and nth particle in state n1. So if you find a determinant of this, then we would obtain the antisymmetric wave function. So if we consider the case of two particles. So for the case of two particles, we would have only this much. So in the place of n factorial, we would have 2 factorial. So 1 by root 2. So here if you see, determinant of this is nothing but n1 of 1 into n2 of 2 minus n1 of 2 into n2 of 1. So this is nothing but this 1 by root 2 n1 of 1, n2 of 2 minus n1 of 2, n2 of 1. So this is the antisymmetric wave function for the system of two particles. So if for the case of n particles, this determinant multiplied with this 1 by root over n factorial. So this is the antisymmetric wave function. This psi a is a solution of equation, and h naught. So this is the solution for this equation they are saying. So h xi is equals to E xi. So antisymmetric wave function. So equation 7 suggests that if two xi's are the same, the state does not exist. The value of determinant 0. That is, here two electrons are in the same quantum state, all 4 quantum numbers, then it's impossible. They cannot have all 4 quantum numbers same. So if in this case we suppose n1 is equals to n2, if we substitute in this determinant, so if n2's, all these n2's are replaced by n1, then this row would be identical with this row. So if there are two identical rows, then the determinant of that particular thing would be 0, would become 0. Hence the wave function would not exist. So that means when both the states are same, when the two electrons are in the same state, that means if they are having all the 4 quantum numbers same, then the wave function would not exist. So that is impossible. So hence no two electrons can have all the 4 quantum numbers same. No two electrons can have them same. So that is the Pauli's exclusion principle. So with the help of this determinant, finally we have proved so why the two electrons cannot be in the same quantum state. So hence the Pauli's exclusion principle, no two electrons can have all the 4 quantum numbers same, is proved from this theory. So thank you.